Your air conditioner is fighting the wrong battle. Right now, on a hot summer day, your outdoor compressor is trying to push heat from inside your house into 95 degrees Fahrenheit air. That is a hard lift. The hotter the air outside, the harder the machine works, the more electricity it burns. But 6 feet below your backyard, the ground is holding steady at approximately 60 degrees Fahrenheit. It has been holding that temperature all year. Through the heat wave last August and through the cold snap in February. If that 60 degrees Fahrenheit earth could cool the air before it ever reached your compressor, the machine's job would become dramatically easier. Some estimates put the electricity reduction at 30 to 50%. The material cost to build the system is somewhere between $40 and $200. There is no refrigerant, no electronics, no special parts, just buried pipe and physics that humans understood long before the first compressor was ever manufactured. A full geothermal heat pump system costs $15,000 to $25,000 installed. What we are talking about does not replace your air conditioning unit. It does something more interesting. It makes the machine you already own work half as hard. So, what is it exactly? How does it work? And why has nobody in the heating, ventilation, and air conditioning industry ever mentioned it to you? To answer those questions properly, you have to go back about 2,000 years to the cities of ancient Persia. 110 degrees Fahrenheit. And the concept of mechanical air conditioning did not exist. The people who lived in those cities were not suffering through the heat and hoping for better times. They were engineering 2:002 minutes around it. They built wind catcher towers, structures called badgers that rose above rooftops specifically to catch prevailing breezes and channel them downward through shafts carved through cool earth before releasing the air into living quarters below. The temperature drop documented in traditional badger structures reaches 15 to 25 degrees Celsius. No compressor, no refrigerant, no electricity, just geometry, airflow, and the stable temperature of deep soil. These were not experimental curiosities. They were the standard infrastructure of cities built in climates that would kill you if you failed to solve the heat problem. The Romans understood the same principle in reverse. Hypocaust systems, underfloor networks of channels and chambers stored earth-generated warmth in winter and released it slowly into living spaces. Different direction, identical physics. The earth as a thermal battery charged in one season and spent in another. Across medieval Europe, root cellars and underground chambers maintain temperatures between 50 and 55 degrees Fahrenheit. Through the hottest summers, not because someone installed a cooling system, but because deep soil does not follow surface temperature swings. It stabilizes. By the 19th century, farmhouses across the American Midwest were already incorporating buried ceramic and brick channels to temper incoming air before it entered the house. This was not folk magic. It was architectural practice based on direct observation of how the earth behaves. These builders were not guessing. They had noticed something real. Below the frost line, soil temperature locks onto the local mean annual air temperature and stays there. They did not need to name this principle in a journal. They just built around it. The knowledge did not disappear because it failed. It disappeared because the industrial era introduced a different way of thinking about comfort. One built around machines you could manufacture, sell, install in a day, and service on a contract. In the 2010s, passive house. Engineers in Germany, Austria, and Switzerland began integrating earth air heat exchangers into new low-energy building designs. Buried loops of PVC or HDP pipe connected to the building's air intake pulled outdoor air through the ground before delivering it to the ventilation system. Measurements from those installations confirmed what the builders of Persian wind towers had known from observation. Ground-coupled pre-cooling worked. It reduced cooling loads measurably. Researchers at institutions including Lawrence Berkeley National Laboratory published analyses confirming the physics. The principle was not new. The confirmation was. The modern application becomes clearest in a retrofit case from the American Southwest. A homeowner in Arizona ran 150 feet of 6-in PVC pipe in a buried loop 6 feet deep, connecting an outdoor air intake to the return plenum of an existing air conditioning unit. Outdoor air enters the buried pipe at 105 degrees. The soil surrounding the pipe holds steady near 60 degrees. Over 150 feet of contact, the air surrenders its heat into the earth. By the time it reaches the air conditioning unit, it has cooled to somewhere between 65 and 70 degrees. The compressor now faces a 37 degrees smaller temperature gap than it would handling raw outdoor air. Electricity bills in summer months dropped 35 to 40%. The inside here was not technical genius. It was simpler than that. The compressor does not know where the intake air came from. It only reads the temperature of what arrives. Give it cooler air and it works less. Here is how the physics actually moves through that buried pipe. Deep soil. Thermal inertia is the foundation. Solar energy and seasonal temperature. Swings penetrate only a few feet into the ground before the Earth's mass absorbs and delays them completely. Below 4 to 6 feet, the temperature becomes essentially constant year-round. When air from a 105 degrees Fahrenheit afternoon travels through a pipe surrounded by 60 degrees Fahrenheit soil, conduction transfers heat from the air to the earth continuously along the entire length of the pipe. The longer the pipe, the more heat transferred, the cooler the exit air. Smooth interior pipe-like schedule. 40 PVC or HDPE matters because rough surfaces trap debris and grow biofilm which can degrade air quality over time. But conduction is not the only mechanism. This is where the system becomes more clever than it first appears. As warm humid air enters the cool pipe, it drops below its dew point. Moisture condenses out of the air onto the pipe walls. This releases latent heat, the energy stored in water vapor, into the soil. The air simultaneously loses heat through conduction, and it loses moisture through condensation. The result at the outlet is air that is not just cooler, but drier. Drier air feels significantly cooler than the temperature number alone suggests because the body's own cooling system perspiration works more efficiently when humidity is lower. The system cools twice. The pipe must be installed with a slight slope toward a drain point so condensate does not pull inside where it would create a mold environment. A compressor handling 105 degrees Fahrenheit intake air draws around 6 kilowatts. The same unit handling 68 degrees Fahrenheit pre-cooled air draws somewhere between 3.5 to 4 kilowatts for the same cooling load. For a household running air conditioning 8 hours per day during a hot summer, that reduction translates into several hundred saved per cooling season. Installations often pay back their material cost within 2 summers. The air that comes through an earth tube feels different from standard forced air. Lower humidity, a faint mineral quality. The compressor cycles less frequently and runs at lower intensity. Fewer start-stop cycles extend the life of the compressor itself, which is typically the most expensive component in any air conditioning system to replace. So why is this not standard practice? The honest answer starts with real limitations. Earth tube systems perform best in dry to moderately humid climates. In high humidity, condensate management becomes critical. If drainage fails, the pipe becomes a moisture trap. The system requires outdoor ground access for burial, which makes it difficult to retrofit in dense urban apartments or homes built on concrete slabs. The inlet air must be filtered to prevent insects and debris from entering the pipe. And the interior requires occasional flushing to remain clean. 10:0010 minutes. This is not a system that replaces air conditioning everywhere in every climate. It reduces the load of an existing system in the right conditions. But the limitations do not fully explain the absence. The deeper explanation is structural. The HVAC industry is organized around certified sealed testable equipment units, products with model numbers, warranty structures, manufacturer liability chains, and service contracts. A buried pipe loop connected to a return plenum does not fit any of those categories. There is no SKU for it. No certified installer classification for it in most U.S. states. No building code category written to accommodate it. Contractors are trained and licensed around specific manufactured equipment because that is what the training and licensing system was designed to serve. Developers build to minimum code and standard product specifications because tenants pay the utility bills, and there is no financial incentive for a developer to invest in a system that reduces operating costs for someone else. Equipment. Manufacturers profit from replacement compressors, refrigerant recharges, filter subscriptions, and service agreements. A buried pipe that halves compressor wear creates no recurring revenue for anyone in that chain. The system was not banned. It was never given a category. The market had no reason to promote what it could not sell on a cycle. If you want to build one, the materials are accessible. Schedule 40 PVC or smooth interior HDP pipe in 6 to 8 in diameter. Use standard drainage rated fittings. Include an insect screen and a filter at the inlet. Include a drain point at the lowest loop. Connect to the return side of an existing AC unit, not the supply side. A minimum of 100 feet of buried length at a depth of 5 to 6 feet. A small solar-powered inline fan can drive it. Passive house builders, earth ship communities, and open source